Everyone. So in this video we want to look on the concepts on quantum mechanics. So for those students who will be studying this paper, you see I've done an introduction to the syllabi that I'll be covering from the beginner quantum mechanics to the advanced quantum mechanics for postgraduate students. So in this video I'll just take you back to the year 1887. Okay, so we are in the classical era of physics. This was the most successful theories, the most successful accomplishments by scientists in this 19th century. Okay, so it was more successful until the scientist by the name Lord Kelvin, to whom the units of temperature is assigned, said there's nothing more to be discovered in physics except more and more precise measurements. Okay, so you see classical physics was more successful at this 19th century, but we'll see in the more couple of years to come, we'll come and see there will be more questions, there will be more experiments coming into the picture to question more concepts in classical physics. So in this year, in 1887, okay, Albert Einstein hasn't came yet to the picture. In this year, the Max Planck, okay, Max Planck hasn't released his postulate. So I'll just take you back. Just answer a question. I'll ask a question and then answer the question. So the question is, what is light? You see, light is something that enables human beings to see. Okay, it enables human beings to see. Once an object reflects the light, you'll be able to see the object. So simply that's the simple definition for light. But you see, in physics, light is more different. Scientists view light in a more different way. Okay, so they in classical physics they defined light as an electromagnetic oscillation. Okay, but in the more years to come, we'll see there exists another world, a very murky world that we are saying light can exist as photons, light can exist as particles, light can exist as waves. Okay, but in classical physics we are saying light is an electromagnetic oscillation. So in this video, with great honor and responsibility to this paper, we are saying our first step is to discuss the classical view of light. Okay, then in the more 10-20 years to come, we'll see light as a particle, light as a wave, a theory that was designed by Victor de Broglie, where we're saying wave-particle duality. So that's the idea that came into the picture to question classical physics. Okay, so our first step, we are saying we'll introduce the Maxwell's laws of light. So these Maxwell's laws of light will enable us to define the nature of light. Okay, the wave nature of light. So in this step, the Maxwell equations are written in a differential form that I'll write. So in this differential form, our next step will take the curl and so much more. Okay, so we are saying we have 4 Maxwell's laws of light that are written in the differential form in this form. So we are saying the divergence, okay, the divergence of electric field, is the same as the charge enclosed in a surface, charge enclosed in a volume, the charge enclosed in a volume upon permittivity of free space. What this shows us, it means the static electric field, it shows the relationship between the static electric field and the charges. Okay, so an intuitive idea or concept to this, we usually say if you have a positive charge, okay, the electric fields emanate outwards. Okay? And if we have, so this is the electric field, it's emanating outwards. If we have a negative charge, okay, the electric field usually emanates inwards. Okay, so the electric field moves inwards. So this is basically the idea behind this concept. So I'll write the second formula. It says the divergence of magnetic field equal 0. What this means is simply the magnetic monopoles doesn't exist. You see, if you have magnetic field moving through space, okay, we usually have two poles, the dipoles. It's associated, the magnetic field is associated with a dipole. So we usually have the north pole and the south pole. You see, if we calculate the net flow of the magnetic field in an enclosed surface, usually comes out to be 0. Basically, that's the second law of Maxwell, okay? So the second law of Maxwell, usually we call it Gauss law of magnetostatics, okay? So this is the Gauss law of magnetostatics. Okay, then this is the Gauss law of electrostatics. Those who have taken a couple courses on physics, introduction to physics, modern physics, we have this relation somewhere, okay? And again, maybe I'll just explain. You see, this Maxwell's equation can be written in terms of the Gaussian surface, you see, in terms of the contour calculus. But for this case, we are taking the differential form of the equations. So we are saying the third law is the Faraday's law of light, okay? The Faraday law of electromagnetic induction. So usually say it's a bit different. So it's the curl of electric field. So the curl of electric field, usually it's given by negative time derivative of magnetic field. Okay. Negative time derivative of magnetic field. What this simply means, it means we can generate, okay, we can generate an electric field by varying the magnetic field. So this is the relation, and according to this principle, this is where this is the principle behind which we have electricity back in our homes. So we are saying this principle, this law lies in the art of our electromagnetic generators. You see, if you have a magnetic field in relative motion with a coil, okay? If you have a magnetic field in relative motion with the coil, you see the change in the magnetic field will result to an electric field, which will result to current. So basically, this is the reason why we have electricity back in our homes, and this is the law of our Faraday law. So this is the Faraday law. This is the Faraday law of electromagnetic induction, okay? Once you have seen this is the third formula, we usually have the fourth formula, which simply is the same as this. So it's the curl of magnetic field given as mu j, okay, plus delta E upon, I'll have to clear this a bit. So it's mu j plus epsilon mu delta E upon delta T. Okay, so simply again, this is another relation, the third relation, that's it relates the electric field and the magnetic field. So you see, you can generate a magnetic field while varying the electric field. Okay, and for all these equations, we are saying electric field can be generated not only by presence of charges, but also can be generated by presence of changing magnetic field. And similar case, we are saying magnetic field can not only be generated by the electric field, but also can be generated by the current. Okay, J here, for those who have taken physics, J is the same as I upon A, of which if we take, if it's in the continuous, if it's the continuous integral, we will take the integral. Okay, but for this paper, we are not diving to that. So we are saying from this point, this law, this is the Ampere law. Okay, so this is the Ampere. This is the Ampere law with added modification. Okay, by Maxwell. Now, once we have these in mind, I will take you back and I will give an assumption. Okay, so all these Maxwell's law are taken in presence of a vacuum. Okay, so they are taken in presence of a vacuum. So this is our assumption that we are taking. Okay, so having this concept, we want to explain. We're saying in classical physics, we have said light is an electromagnetic oscillation, but in the coming years, it will be challenged. This concept will be challenged. We are saying light exists as a photon. Okay, light is a photon. Light is has two nature, has dual nature, has wave characteristics and have particle characteristics. So we are saying we want to understand light in the essence of classical physics, in the essence of the singular nature of physics. We are taking these Maxwell's laws of light in presence of a vacuum. Okay, so once we have these assumptions, I will take you back to our mathematical analysis, specifically vector analysis. Okay, so we are saying in vector analysis, because we are saying we want to see the singular nature of light before it's being challenged in the next 5 to 10 years to come, it will be challenged by Victor de Broglie, by other scientists, or the experimental observations that they took were clashing. Okay, they weren't aligning with what we have in classical physics. So we are saying our first step is to understand the singular nature of light. So in this singular nature of light, we'll do our first assumption, where in these assumptions we are saying take the Maxwell's laws of light in presence of a vacuum, and then using vector analysis, we will borrow the concepts of vector analysis to confirm our idea in proving what is light. Okay, so we are saying in vector analysis we have an identity, that the identity says if I take the curl, okay, if I take the curl of a certain, if I take the curl of the curl, sorry, I just write this, the curl of a certain vector field. Okay, if I take the curl of the curl of a certain vector field, of which our vector field here is A, so I'll say I'll get my answer as the gradient. Okay, I'll take my answer as the gradient, multiplied that by the divergence of the same vector field, which is A, minus the Laplacian. So this is the Laplacian, okay, minus the Laplacian of the vector field. Once we have this identity, our next step is to take the curl of the third law, okay? So if I take the curl of this third law, I'm saying I'm taking the curl of the curl of electric field should give me my answer as the gradient, okay, of the divergence of the electric field minus the Laplacian of the electric field. So basically this is what we have, and remember we have taken the curl of this side, so we must equate it to the curl to this other side. So we are saying this will equal the curl of negative delta B, which is our magnetic field, delta T. So this is what we have from vector analysis. So we are saying we had said these Maxwell's law are taken in presence of a vacuum. Okay, so if they are taken in presence of a vacuum, it simply means no charges. Okay, and also it means no current. So anywhere where these charges will go down to zero, where there is current will go down to zero. From these four equations, you see there is a charge here. This is a charge enclosed in a surface, charge enclosed in a volume, enclosed in a volume, in a closed volume. So you're seeing we are saying it's in the presence of vacuum. So you're saying no charges, so this term will go down to zero. Okay, and again we're saying no current, this term will go down to zero. So that's what we have using this assumption. So we are saying, having this from vector analysis, we'll say the divergence of electric field from this point, after our assumption, we are saying the divergence of electric field will go to zero. So this term will go to zero, and again we'll remain with this term. Okay, this is our computation. We are saying the curl of electric field will give us that, equating that to this. So we are saying we'll remain with negative Laplacian of the electric field should give me this curl. Okay, the curl of this. So I'll take this part of the curl, relate it inside with the magnetic field, and then take the partial derivatives outside. So I'll remain with negative delta upon delta T of now the curl. Okay, the curl of magnetic field. Once we are here, we are saying, so this will go to this. So we are saying, what is the curl of magnetic field? So from here we are saying the curl of magnetic field equal mu naught J plus epsilon naught mu naught time derivative of electric field. So we're saying if this term goes to zero, we'll remain with this part. So the curl of magnetic field will go down to this part. Okay, so I'll replace the curl of electric field of magnetic field by this. So we are saying, replacing that, I'll get negative delta upon delta T, replacing that with this term. So we are saying epsilon, it's mu, okay, it's mu naught. Delta, it's delta E upon delta T. So having that at our hand, we're saying pull out the negative and pull out this term. So I'll pull out epsilon upsilon. Okay, so I've pulled out epsilon upsilon. Then I'll take this derivative and combine with this derivative. You see, it will be the second derivative. So it will be delta squared of electric field, okay, divided that by, if I take also the derivative of time twice, okay, so it's delta t squared. Delta t squared. So that's what basically we have. Then equating that to this Laplacian of electric field. If I take the negative both sides, I'll remain with this, equating that to epsilon upsilon multiplied by delta squared of E divided by delta t squared. Okay, so using vector analysis, we have reached this point. So our next step is, let's indicate this as our first equation. Okay, so this is our first equation that has been predicted by Maxwell's laws of light. Okay, so let's go and take the curl again. So let's take the curl of the fourth equation. Okay, so we'll be taking the curl of the fourth equation. So remember, it's in the presence of vacuum, current is not there, volume charges are not there. So having these, we'll go down and take the curl to this. So we are saying the curl, okay, we're saying the curl of the curl of magnetic field now should give me, from the identity, gradient of now the divergence of magnetic field minus the Laplacian of magnetic field. Okay, so this is our identity. Now from this point, we are saying, let's go back. We have taken the curl to this other side, so we'll have to take the curl to this side. And remember, this term went to 0. Okay, this term went to 0, so simply this term is not there. So we're saying, let's take the curl to this side. So this, we'll equate that to the curl of this side. The curl of epsilon upsilon, it's mu, sorry, delta E upon delta T. Okay, so let's compute that. So once we have these, we are saying, remember we said the magnetic monopoles are 0. So this term will go down to 0. Remember from our first, as I was writing the equations, the second equation says the magnetic equal 0. So I'll take this, my computation, I'll equate this, so I'll remain with this. So I'll remain with negative Laplacian of magnetic field should give me the curl of this term. Okay, so my first step is pull out these epsilon mu naught, then I'll write that delta. Okay, I'll write delta upon delta t, then I'll take this part and then combine it with the electric field. I'll remain with delta, I'll remain with the curl, okay, the curl of electric field. So this is what we are having. And let's remember, let's go back. What is the curl of electric field? So the curl of electric field simply is the negative time derivative of magnetic field of which that's what we'll be writing to this other side. Okay, once we have this, we are saying let's continue to compute what's the curl of electric field. Remember from our third equation we said the curl of electric field is the same as negative time derivative of magnetic field. So we'll take this and then substitute it back to this. Okay, so we'll have, so substitute this to that part. So we are saying we'll have epsilon, negative delta. To this part we are saying negative time derivative of B upon delta T divided that by delta T. Okay, so from this point let's combine our partial derivatives. So you see these and these pull out negative, I'll get negative epsilon mu delta, this delta and this delta goes to delta, then V divided by delta T squared. Okay, so that will equate that to the Laplacian B negative. So going away with the negative, I'll remain with the Laplacian of magnetic field is the same as this negative will go, epsilon mu, then delta squared of B upon delta T squared. Okay, so this is the second relationship that you have gotten from the Maxwell's laws of light. So I'll explain a bit concept to this. I'll take you back for those who have studied the wave theory. If we have a wave, for example, okay, so we can just maybe do it to this side. And so say if you have a wave, okay, we want to compare. If we have a wave, let's say okay, if you have a wave, so that way, and for example this side, if we have a wave that's propagating in space, if you have a wave propagating in space such that this wave has an amplitude of f and is propagating through space in the dimensions of z. So we are saying if we do computations to get the wave equation, we'll get our wave equation in one dimension as a delta f upon delta z squared equal 1 over v squared delta f upon delta t squared. Okay, now this is the wave equation in one dimension. So what if we take it in the third dimension, in the 3D? So if we have 3D of which the wave is propagating in the same fashion as the first wave, okay, but now it's in the third dimension, we are saying we'll get our wave equation as delta squared upon delta x squared plus delta squared upon delta y squared plus delta squared upon delta z squared f, okay, should give me 1 upon v squared delta squared f upon delta t squared. Okay, so if you have this is the 3-dimension wave equation propagating in a similar fashion as the first dimension, propagating in this fashion. Okay, so we are saying we want to do a comparison to this because we are saying the wave is moving through space in this manner. So if you have this, simply take this back. If you compute this is the Laplacian. So this is the Laplacian. Then f should give me 1 over v squared delta squared f upon delta t squared. So this is what our resultant expression. So we are saying from this point we will have our wave comparison. Okay, so we take this first equation that we have gotten and then take this the second equation that you have gotten, compare it to this equation. You see, you will get if we do the relation, you'll get relating magnetic field as this quantity F. You should get it results to this expression. So I can equate this expression to this expression. You see, I can equate this part 1 over V equating to this part. Okay, so if we equate that, we are saying, let's equate that. And again, remember, you can equate this part similar to this part. Okay, so we are saying 1 over v squared equal epsilon epsilon. Okay, so what basically this means is, if we take the value of v this side, so v squared equal 1 upon epsilon mu. Okay, if we take v, we'll get the square root, we'll get 1 upon the square root of mu this. Okay, so we are saying if you compute these constants, so basically we usually have taking the constant. So if you compute this constant, you usually say we have the square root of, we'll have 1 upon the square root of 4 pi times 10 raised to negative 7. We are just including the constant. 4 times 10 raised to negative 7 Henry. It's Henry per meter. Okay. Multiply that by 8.854 times 10 raised to negative 12 Faradays per meter. So if you compute this value, you'll get a value approximately 29, 97, 92, 458 meters per second, of which this is just simply the speed of light. So basically what we have been doing all along is we are trying to relate a wave from the wave theory and the concept from Maxwell's equations. So you see, the Maxwell's equations have predicted that electric field, okay, electric field as a disturbance. You see here, F here is the disturbance, of the wave, the amplitude of the wave. So simply we're saying the electric field as a disturbance propagates through a vacuum with the speed of light. Okay, so if it propagates in a vacuum with the speed of light, simply it's just a wave. That's why we're saying light is a, because light consists of magnetic fields and electric fields that are propagating in a vacuum. Electric field as a disturbance and also magnetic field as a disturbance propagates through vacuum as a wave. Okay, it propagates through a vacuum as a transverse wave. So once we have this concept, we can safely say light is it's an electromagnetic oscillation. Okay, so but after 5 to 10 years, we'll see this concept will be challenged by de Broglie, where we are saying the dual nature of light will be introduced. So from this point, we're saying in the year 1888, Heinrich Hertz experimentally demonstrated that light is an electromagnetic oscillation using an experiment, but this concept was earlier on predicted by Maxwell, and later on in 1888 predicted by Heinrich Hertz. So once he predicted this, he went down and brought about the concept and the properties of waves. So he related the properties of waves and lights to the experiment. So my next video will be doing the properties of waves and properties of light. Okay? So please like, share, subscribe. Let's meet in the next video.